In the next chapter of the material, we're going to be moving into addition of vectors and using vectors to diagram and describe physical systems. But before we do that, we need to make sure that we have a good understanding of what unit vectors are, because unit vectors are what make up all of the vectors that we're going to deal with. Now, a vector in and of itself, as a review, is a quantity with both a magnitude and a direction. So the magnitude being essentially the size of the vector and the direction being which way it is pointing. So in the context of the unit vector, our magnitude is going to be 1. That's the very definition of unity, 1, unit vector, 1. And our direction is going to be unique in that movement in the direction of one unit vector does not move in any way along another unit vector. And we're going to see that as we move into our examples in this video. But the magnitude of a unit vector is 1 and the direction of it is unique. And so moving in that direction does not allow you to move in any other direction. And you need to think of directions as being like the coordinate axes. So let's look at a unit vector in one dimension. So in this particular case here, a unit vector would be 1 unit long in the x direction. Now, quite frankly, 1D is kind of a very boring example, but it is fundamental. No matter how much I move, I might move 2 times the unit length or 3 times the unit length. So in this case, this one here, we denote unit vectors typically by a little hat. This would be 2 times the unit vector, 3 times the unit vector, and so on. I may choose to move -2 times. Negative being a direction, 2 being the number of times, and then the unit vector. So the unit vector gives us the size of the step and the direction of the step. And then we have positive and negative versions depending on which direction we're going on the axis. So let's move into a little bit more interesting example here, and let's illustrate what we mean by unique. In 2 dimensions, we can see how the uniqueness comes about. No matter how much I move in the x direction along the x unit vector, I never have any change. So there is no change in the y direction. No matter how far I move to the left or to the right along the x-axis, it will not change my position relative to the y-axis. Likewise, no matter how much I move along the y-axis, it will not change my position relative to the x-axis, or how far I am left or right on the x-axis. And so in the 2-dimensional case, we have both an x unit vector and a y unit vector. And so if I want to get somewhere in 2-dimensional space, I can tell you to move 2 units along the x-axis and then move 2 units along the y-axis, and you will get to the point that I want you to be at. Now, you'll need to pay attention to the video on vector addition to understand why we can't just combine these things together. These directions are unique. And it's important to note one thing here, and that is the unit vectors along the x-axis and the unit vectors along the y-axis are 90 degrees to each other. This is a term known as orthogonal. And that's a fancy way of saying the cosine of the angle between them angle theta, is equal to 0 because theta is equal to 90 degrees. And that's how you know you have unit vectors, is when you take the cosine of the angle between them, they are exactly 90 degrees. More relevant to us, we can expand this out to 3 dimensions, and this is a straightforward expansion. Right? You have a unit vector in the x direction. This is a right-handed coordinate system, if any of you want to look that up and see exactly what that means. You have a unit vector in the y direction, and you have a unit vector in the z direction. All of these are unique to each other. No matter which pair I choose, I can choose x and y, x and z, or y and z. The cosine of the angle between them is going to be 0. And so we have 3 unit vectors, x, y, and z, in 3-dimensional space. And so movement along any unit vector direction will not change your position relative to any of the other unit vectors. And that's going to be important. Let's illustrate this with an example, and that may help make it a little bit clear. Utilizing our same coordinate system, let's say we want to go climb a tree. And we're going to establish that 1 unit is 1 step by our little guy down here. And we'll just say that his name is Adam. Okay? And so we want Adam, we've told Adam, go climb a tree. Okay? Now, look at our directions on our coordinate system. We have 3 directions. In other words, he needs 3 pieces of information to know exactly where we want him. In particular, this may not be the only tree that's around. So he needs to know which exact tree and how far up the tree we need him to go. And so in this case here, we might tell him to move 27 steps or 27 units in the y direction. If you look at our coordinates there, you should see that this is actually moving in the negative x direction. So we want him to go 4 steps or 4 units in the x direction, but we want him to go in the opposite way. So we want the negative side. And then we got to tell him how high we want him to climb the tree. So we want him to go all the way to the very top. And we want him to go 6 units in the z direction. And so I can give him 3 unique pieces of information. I can give him I can tell him, I want you at -4 in the x direction, 27 in the y direction, and 6 in the z direction. And you will end up exactly where I want you. Now, this is a reverse view so that we can figure out what unit vectors are. But unit vectors, again, are unique directions. They're directions that movement along that line will not change where you are relative to the other axes. And this is important when you start looking at advanced level physics, because there is a connection here. It's not coincidence that 1 dimension had 1 unit vector and 2 dimensions had 2 unit vectors, and so on. When we start looking at vectors, you're going to find out that the number of dimensions is the number of unit vectors that you will have. And no matter what you do, okay, a unit vector, another way to look at it is that the unit vectors are the number of vectors that you can draw that are at 90-degree angles to one another. So I can draw one straight up, and then I can draw one crossways, and then for 3 dimensions, I can draw one this way, okay? And in 3-dimensional space, no matter what I do, I cannot find another vector, I cannot find another direction anywhere that would be at 90-degree angles to all the other directions, no matter what I do. And so in 3-dimensional space, 3 unit vectors or 3 orthogonal axes is all you can possibly have. And this will be very important when we start breaking vectors down into their components in the next chapter.